Welcome to The Explainer. Today, we're tackling a massive misconception in the AI world. We're going to look at why scaling multi-agent AI systems takes a whole lot more than just stringing together some clever prompts. To actually make these things work in production, we need an entirely new architectural paradigm. Let's get right into it. Seriously, picture a chaotic swarm of AI agents for a second. Let's say 5, maybe 10 specialized models all actively arguing over a single complex task. Now ask yourself, if they can all talk at once, why doesn't the whole system just collapse? If they all have their own context windows, their own memories, and their own objectives, why doesn't this just evolve into an endless loop of hallucinations and API timeouts?
Well, here's the answer. A multi-agent swarm is not a chat app. It is a distributed decision system. The actual product you're building isn't the AI agents themselves, it's the state machine that coordinates them. When we move away from those massive, monolithic models that try to do 50 things at once, we have to replace that single brain with a rigid, stateful architecture. One that dictates exactly who speaks, what they remember, and how they hand off tasks.
Okay, Section 1, the market research case study. Let's ground this theory in a highly parallel, high-stakes scenario. Imagine a multi-agent market research firm tasked with generating a complex, multi-layered industry report for a client. We're moving out of the theoretical here and into the highly practical. This specific workflow relies on very deliberate steps. First, an orchestrator handles the task decomposition, literally breaking the client's massive request into smaller, bite-sized questions. Next, specialized agents jump in to conduct parallel research. Then, a critic agent reviews the work for contradictions, a verifier checks the sources, and finally, a synthesis agent pulls the whole shebang together. This sequence proves exactly why a single monolithic agent loaded with 50 tools or just a loose conversational thread between bots instantly fails at scale. You absolutely need specialized workers.
And to structure those workers effectively, you need a hierarchical pattern with crystal clear boundaries. Top-level orchestrators, they don't do the heavy lifting. They delegate to specialized, scoped leaf agents. The orchestrator issues an event. The leaf agent, like, say, a SQL data fetcher, does its one specific job and returns the result. By establishing these hard agent boundaries, we can distribute the cognitive load safely.
Moving on to Section 2, mastering shared state management. To really understand how these specialized leaf agents collaborate without stepping all over each other's toes, we have to shift our focus to the real secret sauce here, shared state management. We have to contrast the messy, unpredictable nature of older frameworks with modern production standards. Look, if you're relying on an unstructured, ephemeral conversational message history where agents are basically just reading a scrolling chat log, you are asking for trouble. We need the clean, highly auditable paradigm of persistent state checkpoints. This means the system's progress is saved as an immutable snapshot after every single step. There's a quote that perfectly captures this shift in mindset. Memory is not a feature here. Memory is the control plane. Think about that. If agents don't share a centralized, intentionally designed state, every single agent becomes its own little isolated universe. And that leads to duplicated work, stale memory, absolutely impossible debugging, and network-wide context saturation. So how do we actually mathematically define that memory? Instead of a messy global scratchpad, the system uses a strict mathematical state representation. Think of it as a centralized tuple consisting of 3 key pieces. M for the core conversation state and metadata, a skill path stack, which acts as a last-in, first-out list of active frames, and finally, the pending skill call, pointing to the next node. This setup provides the exact push-down memory required for recursive tool invocation, which completely avoids contaminating the global dialogue. By adhering to these strict rules of state management, meaning you maintain one single source of truth, utilize immutable checkpoints, require versioned updates, and define explicit write rules, we completely decouple the multi-agent workflow from the underlying reasoning engine. The models just think. The state machine is what actually remembers. All right, Section 3, resolving agent conflicts. Let's get real for a second. What happens when our decentralized, highly specialized workers inevitably disagree on the data they've just found? Let's jump back to our market research scenario. Agent A comes back and says, hey, the market is growing rapidly. Agent B returns and says, nope, the market is completely flat. And just to make things incredibly frustrating, Agent C cites a source that contradicts both of them. Now, if they just keep chatting in a loose thread, they'll literally loop forever. The key insight here is that in a swarm,
Conflicts are not bugs. They are completely expected behavior. Therefore, your conflict handling has to be totally deterministic. You have to build rules directly into the state machine. So if there's a conflict, the system might automatically use confidence thresholds, maybe invoke a dedicated verifier agent to arbitrate, rerun the entire research branch, or, for really high consequence actions, just stop and escalate to a named reviewer human gate. Which brings us to Section 4, failure recovery and checkpoints. Because look, even with perfect conflict resolution, things are gonna break in production. APIs time out, tools return malformed JSON outputs, or a reasoning agent just hallucinates a completely non-existent workflow branch. How on earth do we survive that?
Well, it all comes down to resilience. Because these risk workflows are naturally DAG-shaped, meaning they are directed acyclic graphs with ordered steps, branching conditions, and rejoins, we can easily isolate bad branches. An agent can't just skip steps or create arbitrary new paths on the fly. They are strictly constrained by the graph. And thanks to that last in, first out stack-based execution model we talked about earlier, which, by the way, operates a lot like a push-down automon in traditional computing, we get something incredibly powerful called context-free state resumption. If a node fails, the runtime doesn't have to restart the whole process or flood the chat log with error messages. It can simply retry only the failed node and resume cleanly from the exact last checkpoint. It's a lifesaver. When you look at the current landscape of frameworks, this state model really separates the toys from the enterprise tools. Frameworks that offer persistent checkpoints, like LangGraph, for example, allow for automated recovery and incredible features like time travel debugging. You can literally rewind to a specific node's failure, fix the state, and resume. This is a massive, massive leap over older models relying on ephemeral conversation history, like early autogen or just simpler flow-level states. Let's bring it all home. Section 5, the stateful swarm takeaway. Let's synthesize exactly why stateful architecture is the new, absolute, non-negotiable standard for deploying multi-agent systems into production. A true swarm isn't just about throwing a bunch of LLMs into a room and hoping for the best. It leverages clear roles and boundaries, centralized orchestration, and a deeply integrated state design. Shared source of truth, deterministic conflict resolution, checkpointing, and failure recovery. That is how you turn individual, isolated intelligence into reliable, coordinated, and auditable action. Ultimately, the real challenge in multi-agent systems is not making agents act. Honestly, models are already great at acting. The real challenge is making them agree, recover from inevitable failures, and finish their job with one coherent state. If you don't intentionally design that state, you don't really have a swarm. You just have chaos. So as you look at your own AI architectures, I want to leave you with this. How will you control your control plane?